So, we're going to talk about heat, temperature, and atmospheric circulations this week. Really, we're going to focus on how temperatures occur, why we get different temperatures every day, and what causes that. Last week, we brought in all this energy from the sun. So now we got to figure out how this energy moves around the Earth. How does it move around in the atmospheric system? Well, that is through heat transfer. And there are some consequences of that as well. So let's get some definitions down. So all matter is composed of molecules or particles in continual vibration. And that is a measure of kinetic energy. So the faster the molecules vibrate, the more kinetic energy there is. The slower, the less kinetic energy there is. And temperature is directly proportional to that. So if it's really hot outside, the molecules are vibrating fairly quickly. If it's bitter cold, the molecules are not vibrating as much. So they have less kinetic energy. There's another part of potential energy as well, arising from forces in the atoms, but we're not going to worry about that too much right now. And the heat is basically energy in transit. So, in other words, it moves from one part of the atmosphere to another, one molecule to another. That is a transfer of energy. So that's how temperatures change. So now that we understand a little bit about temperature being kinetic energy, or basically molecules vibrating greatly, what brings the heat to them? What's going to make them vibrate more or vibrate less? And you all want to know the temperature, I'm sure. At least I always do. I like to know what to wear outside or whatever. So one of the things is there's a temperature gradient. So yes, in the poles, it's a whole lot colder than the equator. So which way does the heat flow then? Heat, by the second law of thermodynamics, heat flows in response to that gradient. So which way is the heat going to flow? It always goes towards lower temperatures. In other words, the atmosphere is trying to eliminate that gradient. Any gradient. If there's a gradient across the cold front, the heat is going to try to flow across that cold front and eliminate that gradient. So how does heat flow? Well, there are four basic ways: radiation, which we talked about last week, conduction, convection, and latent heat. So let's delve into those a little bit. Radiation. All right. It transfers energy by means of directly through the atmosphere. It can occur in a vacuum. Doesn't have to be any molecules around. So we learned that again about it last week. And absorption of radiation by an object causes the temperature to rise. The more radiation, the faster the object temperatures will rise. So, and if the object radiates, which some objects do, they're going to cool. Because especially if there's more radiation of energy than there is incoming heat from the sun, maybe. So think about it at night. The Earth is going to radiate at night. That's why the temperature gets colder. During the day, the sun comes in, the atmosphere warms up. So radiation plays a role in the temperature every day. Conduction. Conduction isn't a big factor in the atmosphere, but it does, think about it. If the ground heats up, the lowest layer of the atmosphere is in contact with the ground, so there is some form of transfer from the ground to this atmosphere. The same would hold if the ground is bitter cold. Well, then guess what? The atmosphere is going to try to warm the ground. It's going to take some heat away from the atmosphere, so it actually is going to cool. So that works. Think about it. If you had a bridge across water, there's a tremendous amount of conduction that's going to occur on that bridge from both the bottom and the top. So you're going to lose heat if that air is very cold around that bridge. So that's why the bridges cool really quickly, and that's why you see these signs everywhere. Now, the road, on the other hand, well, it's going to have underneath it soil or ground. That ground probably is warmer than the road and then the atmosphere above it, than the air. So what it's doing is the air is trying to cool the road, below it, the ground's trying to warm the road, so the road is not cooling as fast. So in a temperature is right around 30, maybe 31 degrees or so, and it just dropped to that after a cold front went through, guess what? The bridges are going to freeze way faster than the roads themselves. Another method of heat transfer is convection. And if you add conduction and convection together, you get sensible heating. What convection is, ever watch water boil and you see the bubbles come up? That's convection. It happens in a liquid and it happens in a gas. Air basically rises when it gets hot and then cools, and that cool air then sinks back down. So that is how heat is transferred in the atmosphere many times, through convection. Latent heat, on the other hand, is all about water. Water vapor, ice. So it is the only substance in the atmosphere that changes phase. So that means it changes from a liquid or into a solid, or a gas into a liquid, and maybe even go from a solid to a liquid. Now, we've talked that when that happens, for example, water vapor, temperature is probably going to be a little warmer there, and the molecules are a little further apart than they would be in ice. So in order to go to a water vapor from ice, it's going to have to absorb some heat from the atmosphere. So there's got to be an absorption of heat. Now, on the other way, water vapor to a solid, well, the solid doesn't require as much heat. Or water vapor to a liquid, condensation. Guess what? When you have condensation, heat is actually released into the atmosphere. It actually warms the atmosphere. Now, say you had a very wet period. The ground's extremely wet. What's going to happen when the sun comes back out? Well, you're going to get a lot of evaporation of all that moisture in the ground, right? Evaporation is a cooling process. So the temperature is not going to get as warm. That's why the deserts really get hot, because they get all that heat, because there's no water to do evaporation with. So the heat's just absorbed into the ground, warms the ground. You don't have the latent heat going on there. And that happens in a drought too. The drier the ground is, the actual likelihood that even though the atmospheric conditions are exactly the same as a couple days ago, they're going to be a little bit warmer because there's less moisture. This moisture influences maritime climates versus continental climates. You in Ohio, in that area, or Midwest, St. Louis, wherever, you have a continental climate. So that means you don't have the heat from the water or oceans impacting you very much. You get a very cold winter, fairly warm summer. Now, if you're out in San Francisco where the wind's coming in off the ocean a lot, you don't have a lot of temperature change. The temperature in the ocean doesn't change a whole lot. So that impacts exactly where the fact that there's not a lot of temperature change throughout the year in San Francisco. Here's just an idea of how complicated all these processes are within the atmosphere. Look at the mess that radiation does in the atmosphere, and absorptions and all. Clouds reflect, clouds emit, latent heat occurs. Their absorption in the atmosphere of radiation, greenhouse gases impact it. They send some of the infrared radiation back to Earth. They also emit some back into space. So all this goes into a calculation of what the temperature is going to be at your house. So heat transfer, being conduction and convection, can be measured with temperature change. And when you add in sensible heating, you add in sometimes latent heating as well, maybe with cumulus clouds developing. A cumulus cloud develops means condensation is occurring, heat is being released, so you actually get warmer air in that cumulus cloud. Here is a diagram of how much radiation arrives in different parts. Notice that if you go above 30 degrees north or south, we actually have a deficit of radiation, so we should be continually cooling. We don't. The reason is there's an excess of solar radiation at the equator, and that is being pushed north and towards the southern hemisphere as well. And it helps to balance out. The heat is exchanged through storm systems, the ocean currents, air mass transfer. All of that changes it. Okay, an air mass. What is an air mass? An air mass is a large, could say mass, but large quantity of air, all with very similar characteristics. If you have high pressure sitting over an area, the winds are light. So what happens? The air takes on the qualities of the ground. So say that high pressure is sitting over central Canada. What's central Canada like in the middle of winter? Ice covered, snow covered, fairly dry. So what happens? That air mass gets very cold and very dry. Now, let's take that same idea, transport it down to the Caribbean. What happens there? Well, that air mass is going to be very humid because that is one heck of a warm, humid air down there, and fairly mild. So that air mass is going to be maritime tropical because it is fairly warm. This contrast of air masses is what drives a lot of the weather, and they transport a lot of heat. So that is imbalance is what's causing all of this. And here you can see during the day, we ask you early on, the very first week, why the temperatures in the afternoon get warm, even though the maximum solar radiation occurs at noon. Here's the reason. That solar radiation is continuing throughout the day, gradually building up and continuing so that by late afternoon, the outgoing infrared radiation and incoming solar radiation equal. That is the time of your maximum temperature. Notice that after sunset, you have your warmest temperature. Remember, the higher the temperature is, the more infrared radiation is released. So that means that at that point, you get the greatest amount of infrared radiation going out. Temperature drops pretty quickly early in the evening after sunset. Then as the temperature cools, it doesn't drop quite so fast. The reason for that is that your coldest air, you've got colder, so your infrared radiation has gotten less. So if you have local budgets of heat, some of it can be from bare soil. The more vegetation you have, the better chance it's going to be warmer. Snow can definitely impact it if you have a lot of snow on the ground, like you might in the wintertime in Ohio. Very bright, very reflective, a high albedo. Guess what? You're not going to warm it up very well. And this is just urban heat islands. Very quickly, they looked at downtown Washington, D.C. There is a lot of buildings there, not much vegetation there, and you can see that some areas where there's not much in the way of vegetation and very dry in this condition, when they were looking at it this way, they put out a tremendous amount more heat than maybe out in the suburbs, and especially on the lakes that were around that area. I just wanted to show you one quick little thing here. This is just a surface weather map. We're going to talk about advection. Advection is a key to what's going on in temperatures. Most of temperature change is going to occur through advection. Think about it. Here's a cold front. The winds are north. Behind the cold front, temperatures are in the 60s back up in here and in the 70s down close to it. Ahead of the cold front, temperatures are from the south, and we have temperatures in the 80s and 90s. So there is a temperature gradient right between the two. And you have the cold front moving this way, it's pushing temperatures, colder air in. So if it passes you, temperatures are going to drop. If it comes back as a warm front, temperatures are going to rise. And this temperature gradient drives a lot of the weather. There's a change in air mass. South of this front is a tropical maritime air mass. North of it, continental polar air mass. So here is your transition of air masses as well. You can see this aloft as well. This is looking at 850 millibars, just temperature and wind. and ice and contours. Here are hotter and hotter temperatures out here. The wind's blowing this way. So you can see the temperatures warming with time. If you were in Pennsylvania or Ohio, you're getting warm advection. Temperatures are going to be warming up. Now, just to the north, there's a lot of cold advection going on. So it's interesting to see just how far south this air mass, the continental polar air mass, is going to make it, or whether you're going to stay in the maritime tropical. So this is just some of what's going on in the atmosphere every day to give the temperature at your house. So hope you got something out of that. Please don't hesitate to ask if you have any questions.